Welcome to Chapter 5, the Reciprocal Lattice. So far, in Chapters 1 through 4, we looked at the symmetries of crystals. Now we're going to go into an experimental world where we take a picture, in this case with an X-ray, using X-radiation, of, in this case, a quartz crystal, and we get this beautiful picture. And what does it remind you of? Well, it's a lattice, and what we're going to see is that this picture represents a reciprocal lattice, and upon each point of the reciprocal lattice is superimposed the intensity from the crystal. We're going to discuss this in this chapter. So the reciprocal lattice complements the direct lattice. Just as Alice starts out in the real world, and then in the direct space or the real world, and she goes into the world of behind the mirror, which in our case is somewhat similar to the reciprocal lattice. They're both related, and we know that if we have a clock in the direct space, in the real world, when we go to a mirror image of that clock, we're going to get, it's not going to look exactly the same. Everything will be in a mirror. So in this chapter we're going to compare the direct lattice and the reciprocal lattice and understand the relationship between G and G star. And we're going to calculate properties of the reciprocal lattice, so we can use our G star to calculate B star, A star, and B star, and C star. Now we're going to draw the reciprocal cell superimposed upon the direct cell, and that's what our starter program is going to be. The volumes will be normalized, and we'll see why that is the case. And we're going to relate the reciprocal lattice to the diffraction pattern and the transformations of the direct lattice to the transformations of the reciprocal lattice. And then we're going to show that the Bragg planes in direct space correspond to the lattice points in reciprocal space. And finally, we can use the G star to calculate the D spacings. And as an application of that, we can use G star to calculate the angle between crystal faces. And we're going to relate different sets of lattice parameters for a crystal. So an understanding of the reciprocal lattice is essential to crystallography. It unifies and simplifies the calculations, and it's a physical property, just like any other physical property of density, color, electrical conductivity, for example. Just as the image of a mirror, the image in the mirror, is really a property of that which is being reflected. So, associated with every lattice is another lattice called the reciprocal lattice, and Alice finds that out as she goes through the looking class. If A, B, and C are basis vectors, then let us assume, or let us define A star, B star, and C star, which are the basis vectors of the reciprocal lattice, and they are defined by the following matrix equation. So you can see we have AA star, B star A, C star A, and all of these are going to be equal to the identity matrix. So if you notice, that gives us some special values. AA star, BB star, and CC star fall along the diagonal, so they're all going to be equal to 1. And all the rest of them, such as A star B, are all going to be the off-diagonal terms, and they're going to be defined as 0. We can write this as the dyad dot product. That's really nothing very new, because here we have a 3 by 1 matrix, dotted into a 1 by 3 matrix, and of course we're going to get a 3 by 3, and there it is. And it's of course equal to the diode dot product is equal to the identity. That's the same as what we've just said on the previous slides. Now this is what we're going to do in our quiz. We're going to look at examples in 2 dimensions. So suppose we have A and B, and the angle between them is gamma. Well, we can see that we have all these cross terms. So if you look at A, notice that A star, B star, and C star, and A, B, and C are not equal to 0. So therefore, the dot product or the cosine of the angle between them has to be 0, and that means that the angle has to be 90 degrees. So that means if I go to A, for example, A dot B star is equal to 0 degrees, so they must be 90 degrees apart. So the B star is going to be perpendicular to the A star. So there it is. It looks just like that. And likewise, with the B, we're in 2 dimensions, B and A star is going to be perpendicular to the B. So here we have the B, and then we're going to have the A star coming up perpendicularly. And I expect you to be able to draw this. Let's take some examples. Here's a simple example of A and B perpendicular to one another, and it turns out that A star is going to be perpendicular to B, so it turns out it's parallel to A star and A are parallel, and B star is perpendicular to A, so B and B star are perpendicular. This angle here is 90 degrees, and here's our relationship which is held on the previous page, and we get this very simplified expression that when the gamma is 90 degrees, then A and A star, this term becomes 1, so A is equal to 1 over A star, or A star is equal to 1 over A, and A star is equal to 1 over A, and the same way B star is equal to 1 over B. So you can see this reciprocal relation directly there, and that's where the name comes from, the ideas came from. We can put numbers on this, so if A is a half and B is 1, then A star is going to be the reciprocal of A, so here's A star, so A is going to be reciprocal of 1/2 is 2. The units are such that that when you multiply them out, they have to be equal to 1, unitless, so we call the units of the reciprocal cell as inverse angstroms, and likewise with B. B is equal to 1, 1 over 1 is 1, so we get that equal to 1. So we can see if A is a half, A star is twice that, it's 2, and if B is 1, then B star is going to be also 1. So notice how we have short A and a long B goes to a short B and a long A in the reciprocal world. Now, you see that we have these lattices, and we know a lot about lattices. We've been studying it for the last 4 chapters, and we can write the direct lattice vector is just A, B, and C times some, in this case, integers, if we're talking about the lattice vectors. So the translation vector is equal to U, V, and W, and that's the functionality here. Now on the other side of you start out with the reciprocal lattice, you're going to start out with A star, B star, and C star. They're vectors. You can add them together and form a lattice. The coefficients of the lattice, by tradition in the international tables, are called H, K, and L. We're going to see why a little bit later. And the vector is called capital H. Now, this is kind of strange. You'd sort of expect to see a star in it. I would like to have a star there. Personally, I would put a star there. But we're following the international table, so it's H of H, K, and L is equal to this expression, where the H, K, and L run over the indices from -infinity to +infinity, including 0. Similarly, the U, V, and W does the same thing. We also have a metric G. We have a metric matrix for G, And so we have a corresponding G star metric matrix. We can calculate both. Here's how we calculate the G, and likewise we can calculate the G star. Just put stars on each one of these. We have the A star, B star, and C star, so we can calculate this metric matrix. Likewise, we can look at the volume and the magnitude of the square of a vector and the angle between them. And it's all the same thing. You simply put stars on them. So V star is equal to the determinant of G star, and the dot product of the two vectors becomes, you can see it comes right across. G goes to G star, UV and W sub 1 go to HK and L sub 1, etc. The same thing occurs with the magnitude of the square of the vector, and here's the magnitude of the square of the vector in reciprocal space. G goes to G star, HKL goes to, UVW goes to HK and L. And similarly, we can get the angle between the two vectors in direct space. We know how to calculate the angle of the two vectors in reciprocal space. So you know an enormous amount about the reciprocal space. However, what you don't know so far is the connection between them. And we get that connection by that statement in the very first, one of the earlier slides here. So next we're going to look at the relationship between the direct and the reciprocal lattice. So if we start out with the basis vectors, A star is perpendicular to B and C, and so A star would be, the vector A star would be parallel to the cross product of B and C. The only thing we don't know is the scaling factor. So, but we do know that A times A star is equal to 1. So for the right-handed set of basis vectors, AA star, so we can just multiply AA star, and then we multiply this by A. We're going to multiply this whole thing by A across. We get K times A dot B cross C. A dot B cross C is the volume of a parallelepiped, and so we can just write this as K times the volume. In other words, K, V times K is equal to 1, so K is equal to the reciprocal of V. So A star is equal to B cross C over V. Now we can set up a table where we just rotate these A, B, and C, and A star, B star, and C star, and you can get all of these 6 relationships. And here's Alice climbing through the window, looking at the window and seeing herself in reciprocal space, if you will. The relationship between the matrices G and G star, they actually turn out to have a particularly simple relationship. It doesn't look so simple when you start out. If you have one vector in terms of A, B, and C, and the other vector in terms of A star, B star, and C star, we can take the dot products of both sides, and then we can assemble them in both ways, and we see that we can extract the terms. You can see how we're seeing I think you can see a kind of G matrix forming there. So here we have this relationship of the X star, Y star, and Z star is equal to G times X, Y, and Z. Look at the book for the detailed information on this transformation. So this is a very important transformation. Now the relationship between, continuing with the G and G star, we can set up, we can multiply both sides by G inverse, and we get this relationship here. And on the other hand, if we go back up to the top here and we start with the G star side of the world, we can get the equation. We can get the relationship on the right, and it turns out that G, and here we have G and G inverse, turn out to be equal. So if you want to calculate G star, you calculate G and take the inverse of it. So that's our big relationship that we have so far. Now we want to look at the relationship of volumes. Volume is all about filling up space, and here's Alice when she's in her huge state in this little house where she's crawling around. And we know that the product of two vectors equals the determinant of the dot product of two vectors is equal to the determinant of the product of the vectors. And in this case, the G times G star would be 1, so it would be the determinant 1 is 1. So we can make use of that, and we can see that the determinant of G is equal to 1 over the determinant of G star. But what is the square root of the determinant of G equal to? Well, volume, so we can take square roots on both sides, and we end up with V is equal to 1 over V star. So now we have two big relationships. G times G star is equal to the identity, or G star is equal to G inverse, and the volume being a scalar quantity is equal to the reciprocal. The volume of the volume in reciprocal space is just equal to the reciprocal of the volume in real space, and vice versa, which you can see from this equation here. Now let's just look at it another way. This is what I personally like to do it through vectors. The last way I showed you was the traditional way, more traditional way that you'll see in crystallography books. And here we set up an ABC, and we're going to set up a transformation from ABC to A star, B star, C star. And this is the way that it's a linear transformation. So here are the linear constants, here are the constants, and so here you can set up what they are, and finally we get that the original statement that we got the last time. I think it's just a little bit quicker and a little more elegant. Okay, now this is the summary slide of what you've learned. The coefficients transfer as G, and you can see star to non-star takes you on G, non-star to star takes you on G star. It's important to know how to transform the coefficients, but I don't ask you to memorize this equation because it's too difficult. It's too tricky to memorize. However, the next two are pretty easy to memorize, just that G star is equal to G inverse and G star inverse is equal to G. So you have a matrix, and the reciprocals are related to the inverses, and the volumes are the reciprocals of the volume being a scalar. And then the basis vectors transform in the opposite way from the coefficients. But you don't have to remember that either. Now we want to represent the relationship of the reciprocal unit cell, which is in X-ray diffraction space, if you will, with the direct unit cell. And we can write this in terms of orthonormal coordinates, and that's mainly because we want to look at the C matrix, which allows us to talk to the computer. The computer is strictly an orthonormal guy, and so here we have the relationships. We see that A is equal to C times the 1, 0, 0, B is 0, 1, 0, and C is 0, 0, 1. So here's an example from hexamethylbenzene, and you start out with the ABC, alpha, beta, and gamma. You can set a G matrix, and then you take the inverse of the G matrix, and you'll get the starred quantity. So you can see that's how we go from one to the other. However, I, in my kindness, have given you a starter program that allows you to do it for your own crystal. You'll be using that. It will produce both from the ABC, alpha, beta, gamma. It will produce the A star, B star, C star, alpha star, beta star, and gamma star, as well as the pictures of the superpositions, and we're going to look at that in just a moment. So if we superimpose these, here's the direct lattice, and we superimpose the reciprocal lattice, we just get this little tiny thing, because you can see here A is 9 angstroms and B is about 1/10 of an angstrom, so you really can't see it. And one way of allowing you to see it is simply to scale the constants such that the volumes become equal. So the volume is equal to 1. Find me a pile of a transformation that takes the volume to 1. I've already done it for you in the program, and here we have the relationship of hexylmethylbenzene, and this one that you can't see now becomes quite clear. So let's look at some examples. Here's that's a Cheshire cat up there appearing. So here we have hexamethylbenzene, here's anhydrous alum, and here is a high temperature superconductor. The reason I put that in is because it's orthorhombic, and half of you have orthorhombic crystals, so your crystal is going to look something like that. There's the starter program, which I'm going to put up for you. The new program puts A, B, C, alpha, beta, gamma for your crystal, and you put that in, and it gives you the picture, and it all in the command window. You'll get alpha, beta, A, B, C, alpha, beta, gamma, all starred, G, G star, and V, V star. So I calculated that for you because I'm a nice person. Anyhow, that's all for now, folks. Bye.